an A/B testing of the user interface of an online store was done. And so two variants, A and B, were compared, and the results are that purchase conversion per visitor for the A variant was 4.2% with the sample of 1,100 of visitors, 1,100 visitors. And for the variant B, purchase conversion per visitor was 3% for the sample of 1,000 visitors. So for A version, they had 1,100 visitors and 4.2% purchase conversion. And for B variant, they had 1,000 visitors and 3% purchase conversion. So this means that 4.2% of these 1,100 visitors bought something, so made a purchase, and 3% of these 1,000 also have bought something in this online store. So, and they ask, can we say that the A variant is significantly better? Can we say that that version A, variant A, user interface A, is significantly better than B? Sorry. So I told you that usually the B version is the new one and A is the old one, but it's just a matter of terminology. So here they think that A is better than B. So as we see that this purchase conversion is higher. So the first step is to arrange our data, our observations into a table like the one I have shown you. So we can say that we have two series of trials. So we have the first series of 1,100 trials, and 4.2% of them were successful ones. If we calculate 4.2% of 1,100, this is 46. So we can say that, we have success, failure, we have two series of trials, namely A and B. And number of trials in the first series is 1,100. And 46 of them are successful ones. And so the rest, 1,054, are failures, unsuccessful. And here in the second series of trials, we have 1,000 trials, and 3% of them, that means 30, are successful, and 970 are unsuccessful. And so here we have sums. So and here we have 46 plus 30, 76. And here we have 1054 plus 970. That is 224. 2000 times, sorry, 24. And totally we have 2100, so 2100 trials in both series. So this is the standard representation of our observations of the data. Now we are to formulate our pair of hypotheses. So they say, can we say that A is significantly better? So we have these two proportions, two probabilities, P1 and P2. So P1 and P2 are probabilities that a random visitor of this online store will buy something. Probability of purchase per visitor, for each visitor. And so P1 is probability of purchase for those who were shown the A variant, and P2 is probability of purchase for those who were shown the B variant. And so as they ask, can we say that A is significantly better than B? This means that they are asking, can we say that P1 is greater than P2? So the hypothesis they are asking us to test is that P1 is greater than P2. Is this hypothesis simple or composite? It is a composite hypothesis as it has inequality sign. So simple hypotheses are hypotheses with equalities. So that is why this hypothesis they ask us to test can be taken only as an alternative one. So we have our pair of hypotheses, null hypothesis and alternative one, and the one they ask us to test is the alternative hypothesis in this case. So P1 greater, I'm sorry, P1 is greater than P2. And so what is the null hypothesis? The same but with equality. So now the null hypothesis must have an equality. So if the alternative one is P1 greater than P2, then the null hypothesis is to be P1 equal to P2. Okay, so after we have our pair of hypotheses, so we are to introduce the test statistic. So we say that as a test statistic, we will use this standard formula. So that T is equal to N11 over N1 dot minus N21 over N2 dot in the numerator, and in denominator we have big square root of N dot 1 over N times 1 minus N dot 1 over N times 1 over N dot 1 plus 1, N1 dot, plus 1 over N2 dot. So this is the test statistic. We have all necessary numbers. So now we are just to substitute the numbers we have to this formula. So this will be 46 divided by 1100 minus 30 divided by 1000, and here n.1, that is 76. So 76 divided by 200, 2100 times 1 minus 76 divided by 2100 times 1 over 1100 plus 1 over 1000. So if we do all necessary calculations, we will see that this value is approximately 1.46. So this is the observed value of the test statistic. T is the test statistic, and this is the observed value. Then we say that we know that if the null hypothesis is true, then T follows standard normal distribution. So we repeat this phrase, this expression is the same for all problems of this type, but we repeat this every time we solve the problem of this type to explain why we will use the quantiles of the standard normal distribution for critical regions now. So, and we say that as we have the null hypothesis, this null hypothesis, P1 greater than P2, then we will have right-tailed critical region. So right-tailed critical region. This means that so this is the critical region, and this is the acceptance region. And they are separated by the quantile of the standard normal distribution of the level 1 minus alpha. So we usually Z for the quantiles of the standard normal distribution. We haven't chosen alpha yet, so they didn't tell us anything about alpha. So as we have no ideas why should we use some value different from the default one, let us use the default value of alpha 0.05. Let us say that our alpha is 0.05. Our significance level is 0.05. And so this quantile is quantile of the level 0.95. So this is quantile the level 0.95. And I can use the table and I will find that this quantile is equal to 1.65 approximately. So quantile of the standard normal distribution of the level 0.95 is equal to 1.65, I'm sorry. So now we have the acceptance region and the critical region, and the now we are to see whether our test statistic falls to the acceptance region or to the critical one. And we see that our observed value of t is in the acceptance region. So our t, that is equal to 1.46, is in the acceptance region. So that means that we cannot reject the null hypothesis in favor of the alternative one, and we accept the null hypothesis. So this situation means that we cannot reject the null hypothesis, so it is accepted. So HO is accepted at 0.05 significance level. So now let's give an answer just to the question that was asked. So they say, can we say that A is significantly better than B? So the hypothesis corresponding to this question that was asked was the alternative one. So if we rejected the null hypothesis in favor of alternative one, if we accepted the alternative hypothesis, we would answer yes, we can. And now, as we cannot reject the null hypothesis, and so we accepted the null hypothesis that there is no difference between P1 and P2, that there is no difference between A and B, so then we say that no, we can't. So the answer to the question we were asked is no. So can we say that A is significantly better? No, we can't say so. Maybe I'll write this down even to make it more clear. So no, we can't. And it's better to add the 0.05 significance level. So add 0.05 significance level. So one may ask why it is so. So the difference is not so very big. So we see that the difference is 1.2%. So the difference between these two variants, these two options, A and B, is 1.2%. So this difference is small enough to say that this happened not just by accident. So in case of such a small difference, with 2100 observations, it's better to say that it's more likely that this difference of 1.2% happened just by accident, not because A is better than B. If the difference were not 1.2%, but shall I say 3%, then we would reject the null hypothesis in favor of the alternative one. Or if the same values, the same percentage, so 4.2 and 3, if they were observed not with the samples of 1100 and 1000, but with samples of, let's say, 10,000 and 10,000 observations. If we had totally 20,000 observations, we also would reject the null hypothesis in favor of the alternative one. So if the difference were more than our difference of 1.2%, or if the number of observations were more than the number we have, then the answer would be different. But in this situation, the answer is this.